Good afternoon. Welcome to NASA headquarters. My name is Paula Claggett-Halim, and I'm a NASA Public Affairs Officer. Today we bring you a space astronomy update with news from the Hubble Space Telescope and a review of the telescope's 2 years in orbit by our panel of noted astronomers. Afterwards, we'll take questions. Now our moderator, Dr. Steve Marin, will introduce the panelists. Steve?
Thank you, Paula. We have a panel of distinguished astronomers here today, but before I introduce them, let me tell you what the theme is. We're going to talk about some of the things that Hubble has accomplished in its 2 years in orbit, that an anniversary that we are marking this week. There were some early disappointments with Hubble telescope. Everybody knows about them. But those days of blue gloom turned into some weeks and months and now 2 years of what I might call true grit, as teams of astronomers, spacecraft operators, engineers, mathematicians have all pulled together and figured out how to restore, or as we call it, deconvolve the pictures from the Hubble Space Telescope to get the maximum out of them and to correct the other data from other onboard instruments. And as a result, we've had a lot of terrific findings. We'll have a retrospective of some of the favorite findings of our panelists during this show. And we're getting new stuff from the Hubble telescope every day, day in and day out, and we'll have a few examples of new findings that we'll show you for the first time today. Now, we have as guests today on the third edition of Space Astronomy Update, starting on your left, Dr. John Bacall from the Institute for Advanced Study in Princeton, New Jersey. John Bacall is one of the people who made the Hubble telescope happen, with testimony to the United States Congress, in his leadership role at the National Academy of Sciences, and more recently as the president of the American Astronomical Society. He's an interdisciplinary scientist working with the Hubble telescope. Welcome, John.
Thank you.
Next to John and next to me, Dr. Sally Heap. She's from the Goddard Space Flight Center in Greenbelt, Maryland, where I work. Sally Heap played one of the principal roles in building and operating the Goddard High Resolution Spectrograph, an onboard Hubble instrument that is the most powerful ultraviolet spectrograph ever operated in space. Just to my left is Dr. Dan Weidman. Dan is an infrared astronomer who's professor of astronomy, Pennsylvania State University in University Park, PA. And Dan is an investigator of galaxies and quasars, and we're making him into a solar system pundit today as well. And next to Dan, our other veteran Space Astronomy Update panelist, Dr. Bruce Margon, chairman of the Department of Astronomy at the University of Washington in Seattle, one of the people who helped build and is observing with the faint object spectrograph, another one of the 5 instruments on board the Hubble telescope. Welcome to the panel, and now let us talk about a recent finding from the Hubble telescope. The weekend of February 8th, as the interplanetary spacecraft Ulysses went by the planet Jupiter, making measurements of X-rays and particles and magnetic fields, but without the capability to take photographs, the Hubble Space Telescope made the first ultraviolet photographs of the auroral oval near the North Pole of Jupiter. The research was done by Dr. John Caldwell of York University in Ontario, Canada, and our producer, Trish Pengra, took a crew up there last week, and here is an interview with John Caldwell telling us what he found on Jupiter.
Good afternoon. Today I want to present the first ultraviolet image of the aurora on Jupiter taken by the Hubble Space Telescope. The Jovian aurora is similar in many ways to the northern lights, which are familiar here on Earth. In both cases, it's what happens when very high energy particles, which are trapped in the magnetospheres of the planets, impact on the upper atmospheres. Literally, they cause the atmospheres to glow. The Hubble image was taken simultaneously with the flyby of Jupiter by the Ulysses spacecraft. The data sets between the two spacecraft are complementary. The Ulysses payload included many particle and fields experiments, and the Hubble was able, from a distance, to get the big picture. Ulysses doesn't have a camera on board, and of course Hubble does, and the Hubble cameras work very well. In this case, simultaneity is very important because the aurora is always changing, and it is just not good enough to make observations of one kind at a particular time and then make another kind of observations later and try to compare the two. The aurora has a lot to tell us about the polar environment on Jupiter, including the temperatures there, the winds, and the chemistry. Now that we have the data, we're very excited by the prospect of combining the information from the two data sets to learn a lot more from that combination than we ever could from just one set alone.
That was the auroral oval on Jupiter. We have an auroral oval over the north magnetic pole of the Earth. If you go to Norway, for example, which is under the oval, you see an aurora every night. But the auroral oval on the Earth, I think, is probably very different from the one on Jupiter. Dan Weidman, what can you tell us?
Well, the first thing I'm going to do is start with a bit of an apology. I'm apologetic from the fact that we have so many exciting things to talk about today that we really can't do justice to this recent observation or other observations that Hubble's made of objects in our solar system. But this aurora is a quite unusual thing in contrast to the one you mentioned that's associated with our planet. For one thing, it's much, much larger. The planet Earth would just about fit inside that circle of aurora we just saw on Jupiter. But I think more interesting than that from a scientific point of view, this aurora on Jupiter is caused by a totally different phenomenon. In the case of the Earth, the northern lights come about when particles from the sun are channeled into the north and south pole of the Earth by the Earth's magnetic field. In the case of Jupiter, those aren't particles from the sun that are stirring up the glow that you saw in that aurora, but in fact they're particles from Jupiter's closest large moon. The moon Io is being tugged upon and distorted and heated by the gravitational pull of Jupiter, and as a consequence, there are these very active volcanoes on Io, which are spouting off all the time, erupting, loosing particles in the vicinity, and those particles get trapped by Jupiter's magnetic field, and it's those particles that we see channeled down and crashing into the pole of Jupiter. So what we're really seeing in this aurora is one of the few visible manifestations of this delicate dance taking place between Jupiter and Io, and it's all controlled by the extraordinary magnetic field of Jupiter in that vicinity. So, interesting phenomenon. I'd like to have more time to talk about it today.
Well, if that theory is right, and I think that the observations John Caldwell got will enable he and his colleagues to determine, in fact, whether this current theory of the origin of the aurora on Jupiter is correct, and it has been debated among the planetologists. As I understand it, the pictures that Hubble got should be capable of answering that question. And if that theory is right, this will be one of the very few forms of light other than man-made or person-made light in the solar system that is not powered by the sun. This is light that ultimately derives its power from the gravity of Jupiter.
This glow would be there no matter where Jupiter and Io were. They could be totally removed from a sun, from a star, and this glow would still be there, shining.
There have been a lot of Hubble studies of the planets. Most of them have not come out yet, or at most in preliminary form, because they tend to be long-term studies. With the Ulysses or with the Voyager, you get some great data, but you go by the planet in a few days. Hubble keeps looking. And we probably won't talk much more about it during this show, but at the end of the show, in fact, after the question period, we will show a videotape prepared at the Space Telescope Science Institute that remind us of many striking images that have come down from Hubble in the last 2 years, and this includes quite a few of the planets. Now, to go to another subject entirely, Bruce Margon, one of your fascinations is with globular star clusters, and Hubble has turned out to be just an incredible way of studying those objects. What are globular star clusters, and what are we learning?
Globular star clusters, Steve, are objects that are very well known to the amateur astronomers. There aren't any in the sky that are quite bright enough to see with your naked eye, but a small telescope will show them just splendidly. If we could have our first still picture, I'll show you what one of them looks like from a ground-based photograph. A globular cluster is an agglomeration of 100,000 normal stars, each one about as heavy as our own sun, that are trapped together by their own gravity, tugging on each other, swirling around like a beehive, unable to get away.
And this is not a Hubble photograph.
This is not a Hubble photograph. This is a ground-based photograph. And although it's beautiful, it also instantly shows you the problem, or one problem, with studying globular star clusters from the ground, and that is the stars are so close together that all ground-based images, especially towards the center of the cluster, are just hopelessly burned out and overexposed. So there were always high hopes that Hubble would tell us new things about globular clusters.
That there are two stars lying on top of each other, so you can't...
In fact, not two, but 2,000, right, in each little place. Now, globular clusters are neat because they're an experiment by nature in gravity. That is, you have 100,000 little particles, each one obeying Newton's law, each one subject to the tug of 999,000 other ones. And in fact, although Newton's laws are simple, there are so many stars in a globular cluster that even the fastest computers we have today cannot track specifically how this
They don't just
gravity
go
will
around in
evolve.
circles or even ellipses.
Well, like a single star might if left to itself, but of course there are these constant involvements with nearby companions. And so the clusters have always fascinated astronomers because we realize on a timescale of 10 to 20 billion years, the age of the universe, that they're going to evolve, they're going to change because of all these interacting forces. But they are so complex, just because there's so many stars, that you can't calculate what this evolution is going to be very easily. There have been suspicions that the evolution might end in some, or possibly even all clusters, with a collapse into the center, into a massive black hole.
There you go again.
Black holes rear their ugly head again, it's true. But they were only suspicions, okay, really unverified. The problem really being it's very difficult to observe deep into the center. Let's take a look at the next still, and I believe that we'll see one of the first images of a globular star cluster. This is just a teeny little piece of it.
That's very confusing.
Well, what we see on the left is a little piece of a globular star cluster taken from the ground with a large telescope with a conventional instrument. And on the right, we see that identical little piece of the same star cluster imaged from the Hubble Space Telescope. And as you say, you look at those two panels, I mean, they don't even look the same. But if you look carefully, you notice over there on the far right, there is this blurred out arc. That's right.
On the far side, which is the same in both.
Each little blob on the ground-based photograph on the left, the HST then breaks up into dozens of individual little stars. And so for the first time, instead of just seeing these horrendously overexposed blobs from the ground, we're actually looking into the heart of the cluster and seeing the individual stars and seeing what's actually going on in the center.
Have you learned things, though, just from the imagery? Do you need more than simply these pictures? to tell
He's
you-
glad you asked.
I'm glad you asked that. Right? These studies are still at a preliminary stage, but even just the images are immediately telling us certain interesting things. I believe the next still image is one of these results in a globular cluster called M15, because it's from someone Messier's list of funny nebulous objects, entry number 15. And this was a cluster which, from the ground, was thought was going to be a prime candidate for a black hole in the center.
This is the center as seen by the Hubble
This
Space
is the
Telescope.
very center of the cluster, as imaged by the Hubble Space Telescope.
Told you they weren't.
Well, a picture is worth 1,000 words here, and what you see is a bunch of stars, a bunch of dots, no central light cusp that's caused by the attraction of a giant black hole that's causing the stars to swirl around it. And so in this one picture, that subset of astronomers who thought there was a massive black hole in M15 have largely backed off. There is no evidence for one giant central attractor there.
But still, it raises new questions. It's kind of like the Sherlock Holmes story where the dog didn't bark. There's got to be an explanation, and we hope someone's going to come up with one of these days.
Well, there is some observational evidence to what these interactions do. The next still, I think, will show us that in the center of a different cluster, as imaged by the Hubble Space Telescope, we are beginning now to find evidence for a very peculiar population of stars. This is a star cluster called 47 Tucani. It's only visible in the southern hemisphere. And the bright blue stars that you see, we're just looking at the very, very center of the cluster here, just a teeny little piece. And these brightest blue objects turn out to be very peculiar stars that are hot and young, even though globular star clusters are thought to be the oldest objects in the universe. They're thought to have only very old stars. Yet now when we can finally peer into the center using HST and look at each individual object, we instead see these young stars. And we're beginning to realize that maybe we don't get romantic black holes from collisions of stars in the centers of globular clusters, but rather we get these stellar rebirths, these merging of stars, which cause a new population of hot stars to be born. So there's a lot more work to be done, but the initial evidence is that HST is going to tell us an awful lot about what's going on in the very center.
And found these
of
were
globular
mostly
clusters.
in the center of the cluster.
That's right, in the very
Why
center.
is that?
Well, they're the most massive stars, and so they tend to kind of sink to the middle. Like if you put some marbles in Jell-O and waited a while, they'd very gradually sink to the center of the Jell-O.
Okay. Well, Sally Heap, Bruce Margon's been talking about the globular clusters he's been studying. These are huge aggregations of what are mostly very old and relatively medium and lightweight stars. And the pictures we've seen, those are all globular clusters in our own galaxy, the Milky Way. You have been studying a totally different kind of star cluster that composed of, I don't want to give it all away, but it is in another galaxy, 169,000 light years from Earth. Tell us about your favorite star cluster.
Well, Steve, Hubble has looked at some real stellar nurseries too, as well as these old clusters. And one of the most interesting ones that it's looked at is an object called R136a. That's in another galaxy, as you say. It's in the Large Magellanic Cloud. And as recently as 10 years ago, people thought that this might be a supermassive star. It might be 2,000 times heavier than the Sun. Well, in August of 1990, the Hubble took a picture of R136a and immediately put that theory to rest. It was obvious right from that first picture that this was a cluster of stars, not just a single star. Well, since that time, the Hubble has gone back and taken more deeper exposures, and we've been able to measure the brightnesses of stars in the cluster. And I think the still picture has a picture of R136a is taken from the Hubble. On your left, you see a picture of R136a, a region only 1 6/10 light years across. And the left part shows you the R136a cluster as the Hubble saw it. On the right-hand side, you see it after a technique that we've called photometric reconstruction. That shows R136a as Hubble will see it after the first repair mission.
This is the latest word in these various techniques that mathematicians and astronomers have been developing to
It's
sharpen
one of the
pictures.
techniques. And it shows quite clearly that there are nearly 50 stars right there in R136a. And we can measure the brightnesses of those stars, and that's fine. But you still need to have more. You want to know how hot they are. You want to know how heavy those stars are. And for that, you need spectra. And so the Hubble went back still another time to R136a, this time taking a spectrum of it. And I think the next still picture shows a portion of the spectrum that the Goddard high-resolution spectrograph
What do you
took.
study on there to find out how big these stars are?
Well, what we study are the features that were formed in the outflow from these stars, or the winds from those stars. And that big feature on the right-hand side,
big dip around
the big dip and the big
15,
emission
15.
there, that was formed by triply ionized carbon from the outflows from these stars.
And Sally, this very brief description you've been able to give us illustrates one of the frustrations of trying to explain things the way we do, because we like to show pretty pictures. Pretty pictures are very impressive, especially in this case, they were dramatically impressive. The one you showed illustrating 50 stars where before from the ground we thought there was only one. And yet when the time comes to really do the scientific analysis,
real physics.
you've got to do the spectrum.
You've got to have the spectrum. That is so informative. And right away from that spectrum, combined with the pictures, then you get the full picture. And what we find is that these stars are very heavy. Some of them are 100 times heavier than the Sun. And what is even more striking is that the heavyweights outnumber the lightweights. That's completely different from any type of cluster that we know in our own galaxy.
Yeah, it's really worth emphasizing this. I just saw last night for the first time your paper on this result. And it's an example of the kind of thing that is truly a new discovery, a new scientific discovery with Hubble, in the sense that you found in this particular group of stars, you found a situation where it appears to be just as easy, maybe even easier to make large stars than to make small stars. And that's totally counter to all the assumptions we've ever had in astronomy about the way stars are made. It always assumes that we made a lot of little ones and just a few big ones, but you're showing us a group of stars where it's mostly very large, very massive stars.
Well, before, as you say, we had to make assumptions. Now Hubble gets a picture. Now Hubble gets a spectrum, tells you what it's like. Now you can't make that assumption anymore.
Okay, I think to give credit where credit is due, because this is an important finding, we knew before Hubble there was probably more than one star, and the story kind of goes like this. Quite a few years back, observers in, I believe, South Africa found this star, and at that time it was just listed as one star. In the late 70s, a smaller NASA satellite observatory got evidence that led most of the people who looked at it at that time to suggest this was a single star with an incredible amount of mass that violated the rules on how massive a star could be. This looked like an amazing finding. Stars shouldn't get much more than 100 or 120 solar masses, because then they're producing so much light that the pressure of the light blows the outer layers of the star part. And I remember writing an article at the time saying not everyone agrees with this, but I think even if it turns out that it is not a supermassive star, which was the party line at the time, it would still be an amazing thing if in a size it turns out you showed us just 1.6 light years. It's a little bit more than just the distance 1/3 the way from the sun to the nearest star. You've got 50 stars packed in there, probably all much larger than the sun. So I think that's extraordinary finding. And we could go on about it, but I'd rather hear about Sally's next finding. This is one of the best pictures, I think, if I may say so artistically, to come out of Hubble. I think it's someone that's going to go on a lot of walls, and it's a real hot star. Tell us about that.
That's right. It's an absolutely hot star, and it's also very old.
Is it in fact the hottest star, Sally?
Wait, there's a story behind it. Yes. This is an example of a type of star called the central star of a planetary nebulae. These are stars that are very much like the sun, but they're very much older, much more evolved. Legally speaking, they're practically dead. But in these last phases of their lives, they go through a blaze of glory. This is, in Andy Warhol's terms, their 15 minutes of fame. They really are spectacular. They have sloughed off envelopes, and I think we have a still picture of NGC 2440, and all of that red and yellow and streamers and blobs and everything. That originally was part of the star, and it sloughs that material off. And the interior part, that little white dot there, is the star. Well, you can see it easily, but on the ground, I've never been able to see it for real. And in fact, we took this picture so that we would know where to tell the telescope to point the next time when we came back to get a spectrum. And this illustrates the problem that we had, that these most spectacular cases where you have extremely hot stars, they're very faint, and besides that, to make it worse, you're seeing them against the glow in the nebula. You can't pick them out. But with the Hubble, we were able just to see it right away, and we even could make measurements on it to find out how hot it was. And as it turns out, it's at a minimum of 200,000 degrees Celsius. So this, as far as I know, is the hottest star on record that we know of.
I think we'll submit that record for the Guinness Book, but I'm being told that we're running a little bit behind. I want to alert the controllers that we're going to skip the supernova and continue maybe with the theme of star clusters. We've heard from Bruce Margon about these remarkable new findings about the interiors of clusters of very old stars. We've heard from Sally Heap about a very strange kind of cluster that we have yet to fully understand, densely packed, very young and massive stars. But there's still something else that Hubble, one of Hubble's greatest hits, it's one of Dan Wiebman's favorites, and that's a case of what may be newborn, old star clusters. What is that about?
Well, let's try to explain it a little more thoroughly and take some time to look at the next picture. I believe in our most recent show, just 10 days or 2 weeks ago, we talked about some things happening in the centers of galaxies, and I didn't want to reproduce some pictures we showed you at that time. It turns out, however, in this case, we are once more looking into the center of a very active, unusual, explosive galaxy, which happens to have a quasar in it. And the quasar, which is the center of the galaxy, is just to the upper right of center in this picture. The brightest blue dot you see actually is light shining from a quasar buried in the center of the galaxy, but that's not what we want to talk about this time. What you should concentrate on in this picture are all those other blue dots. Blue dots all over the image. They're sort of immersed in with some multicolored darker material. And that darker material probably is the leftovers of another galaxy which once upon a time collided not so long ago with the galaxy that contains the quasar. And by some extraordinary process, that collision stimulated the formation of large numbers of clusters of stars. And each of those small blue dots you see apparently is an individual globular cluster born not so many hundreds of millions of years ago. Now, this is an example of one picture. It's probably the most dramatic case in Hubble, actually, of one picture which totally changed our way of thinking. What happens is that we have normally, conventionally, in the usual paradigm of astronomy, thought of the globular clusters as the oldest groups of stars in the universe, groups of stars which somehow represented the skeleton of galaxies that formed in the very beginning. And yet now, here we see before our very eyes a whole system of globular clusters forming instantaneously and not so very long ago. Very recently, in fact, as far as time in the universe is concerned. And what that tells me is that we may have been very wrong about our theories of entire galaxy formation. It may be that galaxies didn't primarily form at one instant 15 billion years ago, but that in fact the formation of galaxies, the formation of the structure that we recognize as galaxies, is something that's ongoing. And just one picture can change your way of thinking about this. And when I saw that group of globular clusters, having formed fairly recently in the vicinity of a galaxy, I suddenly realized that the way I'd been thinking about globular clusters all these years wasn't completely right.
Well, I think, first of all, it's a terrific illustration of the fact that you find, I think, in just about every field of science, you certainly find it throughout astronomy, modern astronomy, especially as we look out in new windows on the universe and the different forms of radiation that satellites allow us to observe. And the radio telescopes on the ground did this before we had a space program. And that is that when you find the thing that you're not looking for, that's often the biggest surprise of all. You mentioned how one picture can completely change our thinking, and we do have a distinguished theorist on my far right. We're going to get to him before long and ask him if one picture is worth 1,000 theories or not.
Which of his theories were wrong?
And getting to John Bacall, no astronomical briefing is complete before the cosmologist sings, and John Bacall has been humming along.
I don't think you want to hear me sing. My kids don't want to hear me sing.
John Bacall has been doing some groundbreaking, if I can say that, of a space-based telescope investigations of the larger universe around us, and of course no such study is complete without looking for dark matter. And tell us a little bit about what you've been doing, John.
Well, we've been looking for dark matter in two ways, Steve. Both of them use quasars, which are very far away. In the first one, we've looked when the telescope was otherwise idle at over 350 quasars, which are very far away. And we use them like flashlights to illuminate the material along the line of sight between us and almost the edge of the universe. And we look for what Einstein taught us was lenses being formed by gravity. Einstein taught us that gravity can form a lens in the same way that your glasses and my glasses form lenses. From ground-based observations, which did not have the clarity of the HST images, we thought that when we looked at these quasars, we would see something like 1 in 4 would form multiple images because gravity would pull on the light and make multiple images. But if we see the first of the still pictures, we'll see a color picture, and you see it right there, a color picture of an object that's almost at the edge of the universe when the universe was only a few % of its current age.
These are 4 different pictures of it.
This is 4 different pictures in 4 colors, because Einstein told us that gravity is colorblind. So if it's really a lens formed by gravity, then the ratio of the intensities in those two images ought to be the same no matter what the color is. And that was one of the key tests to show that this was...
That, I guess, is how you know that the little guy is not just a foreground star.
That's right. We've subsequently taken spectra of these, both the small and the large image, and see that they have the same distribution of light. But already in the four colors that you saw there, we knew that it was an Einstein lens. And so we're using these two objects, which are very far away, to tell us how much there is between us and the edge of the universe.
But you said, according to your latest count, you said you've looked now at 350 individual quasar targets trying to find evidence of gravitational lensing. And is this still the only one you found?
Is this a Hubble hit or a miss?
This is a fantastic hit. This is a big surprise because with the imperfect pictures that we saw from the ground, we thought 1 in 4 would form multiple images.
But in fact, you found 1 in 350.
1 in 350. So that's,
what does that tell you about dark matter out there?
Well, that tells us that there is not a lot of it in the form in which it could form images, in which it was condensed,
concentrated
into the center so that the gravity would really pull hard on the light that came nearby. And that's already showed another result, which is of relevance to something that Einstein proposed in the 1930s, that a constant that he introduced to describe how the universe developed in time, that constant must be much smaller than many theorists had speculated.
And here comes the dread term, lambda-dominated universe.
You don't have to say that, because are you saying that these observations rule out a universe which is continuing to accelerate?
The Big Bang getting faster and faster.
This rules out the extreme versions of that which have been suggested recently and makes that untenable, because if there were universes of that kind, we would expect not to see 1 out of 350, but something like 40 or 50 out of 350, and we didn't. So that's just completely out. That theory is one of the theories that we can put in the waste-space paradox.
Actually, it's also a beautiful illustration of how sometimes not seeing something can be just as important as seeing something once you understand well enough how your instrument works.
It's a very clear result, and one of the results which, when we were advertising what Space Telescope would do, we never envisioned this way of observing, and we never envisioned attacking this problem.
We didn't know the gravitational lenses actually existed observationally when Hubble was being designed.
And at least in the early stages. Excuse me. The picture we've just seen, many of the science writers in the NASA auditorium here, NASA headquarters today, have seen before. That was announced a few months ago. But John, you have recently completed a new study of the so-called Hukra lens, a very elaborate gravitationally lensed image. And you've made a measurement with Hubble of a precision that's unprecedented in the field. Tell us about it.
3 of us in Princeton, Hans Walter Rix, a young German astronomer, Don Schneider, who's also at the Institute, and myself, have studied this image which John Hukra found. John Hukra, as you know, has the Midas touch. If you were...
He's an astronomer at the Smithsonian Astrophysical Observatory in Massachusetts.
That's right. And John found, to his astonishment, that he had in one of the galaxies that he was looking at, he found a quasar which is very, very much behind a nearby galaxy, almost lined up at the center of the galaxy. And if you were God and just throwing quasars behind galaxies at random, you'd have to make 3,000 universes at least before you would make a case this beautiful.
A perfect lineup of the Earth, the galaxy, and the quasar far beyond it that the galaxy is gravitationally lensing.
And I hope we'll see this picture now. This is a picture which you'll get to see because at the Institute for Advanced Study we're currently having an art show which is going to be judged. And we took advantage of our HST picture to make something which we thought was beautiful, and I don't know how the judges are going to...
Tell us what's what. What are these white dots and what's the red circle?
Well, what have you measured?
Right. And first of all, the big blue thing is a spiral galaxy, which is very nearby. The 4 white dots, which are almost concentric with the central white dot, those 4 white dots are images of the same distant quasar. And the central white dot is actually the brightest point in the center of the galaxy, slightly off-center from the 4 points of the quasar image, and the red is just the internal part of the galaxy. And the 3 of us have measured the amount of matter that's in this central image, because we can tell how far away and what the relative brightnesses of those 4 images are in this central
The
part.
idea is that the quasar light essentially passing through this galaxy has been bent in its path
That's
by
right.
the gravity of the galaxy.
That's right.
And by determining the amount of that bending, you have measured very precisely the gravity of the galaxy using
Precise.
only the light from that quasar.
That's right, and we've been able to measure the mass within the central region of this galaxy to an accuracy of 2%, which I believe is the most accurate measurement made in extragalactic astronomy of the mass of another galaxy.
How massive is it?
It's a little bit more than, in this central region, is a little bit more than 10 billion solar masses.
With that figure to contemplate, I want to notify our director, Carl Bennett, that we're continuing to be a little bit behind schedule. We're going to skip the 2 cartoons.
They weren't funny cartoons anyway, so.
Probably just as well. And go on to another area where 2 teams using the Hubble telescope, one of them led by John Bacall, and he in particular has used a faint object spectrograph, an instrument that needs to be mentioned now and then. And you've been studying the so-called intergalactic hydrogen clouds, if that's what they are, and you've learned some basic new properties of this unusual and little-known component of the universe, but it's not clear whether you've answered a question or raised some. Tell us a little bit about that.
Well, right. I think, Steve, I'd like to begin just by differing with how you described what Space Telescope is doing and what this 2 years have been like.
Okay.
I think this retrospective is very much like a kid's birthday party, where every kid gets some really spectacular presents in his pack to take home. But no kid knows what he's going to get before he goes to the party. And in this case, we expected to observe what people had seen at very distant times, at very early times and at very great distances, primordial hydrogen clouds, but very few of them with the Space Telescope. In fact, our first surprise, and it was our first present, was that there were more than 10 times as many clouds of that type, hydrogen clouds, as we would have expected from extrapolation. The second big surprise, and one which we just recently glimpsed, is that instead of being the building blocks of all of structure, the galaxies, as is the common explanation for what's seen far away, we found with Space Telescope, when we could look nearby at these clouds that we were seeing, that they were associated with galaxies. So not only are there very many more of them than we had anticipated, we also found that they're associated with galaxies in cases in which we can check. And it looks like galaxies have absolutely huge halos, maybe the remnants of gas that's left over when the galaxies were formed. So this has been completely unanticipated, a wonderful bonus to what we had hoped to see, and we're just unwrapping our presents now to find out what it is that we've really discovered.
The search strategy there being to observe, again, a distant quasar and look at something that's happened to the light as it came to us. And in this case, what's happened is the light's been affected by intervening clouds of material which you couldn't otherwise have seen.
That's right, and it's absorbed, and where it's absorbed tells us where the material is. And then with ground-based observations, we followed up and found in some cases that there were actually galaxies there.
Well, I think Hubble looks far out, and we certainly could go on forever talking about it, but all good things must come to an end, or at least to the question period. And let me just sum up for a minute before I turn it over to Paula Cleggett-Halim. What we've seen is there's a lot of terrific stuff that's come out of the Hubble Space Telescope in the last 2 years, and some of the new findings we learned today are the first accurate measurement of the central core of the galaxy. Turns out to be 10 billion times the mass of the Sun. We learned about one of the hottest stars in the universe, clearly resolved from its bright surrounding nebulosity for the first time, and Sally Heap told us that star has temperature about 360,000 degrees Fahrenheit or more. Sally also showed us the clearest view yet of one of the most unusual star clusters in the universe, R136a, where 47 or more stars, probably all of them much more massive than the Sun, are packed within a radius of 0.8 light years, or from one end to the other of the picture she showed us is just a little bit more than 1/3 of the way from the Sun to another star. And on the videotape, we saw Professor Caldwell from York University in Ontario, York, Ontario, Canada, telling us, giving us a first glimpse of Hubble's first ultraviolet photographs ever made of the northern or either auroral oval on the planet Jupiter, the kind of information that picture contains, and its correlation with the data in the Ulysses space probe may enable us to tell what drives the northern lights on Jupiter. And Paula Cleggett, back to you.
Thank you. We can now take questions. Please state your name and affiliation before asking the question, and please wait for the microphone. Get you on the back here.
Phil Chen, Earth News. I guess for John Bacall. After the spherical aberration was discovered, we were told that it'd be not until after the M&R mission that we'd get a better figure on the Hubble constant. But everything you're telling us is that you're getting some indirect methods of getting in much closer than what we have before. Until now, I've heard between 50 and 100 kilometers per second per megaparsec. Can you narrow it down any closer?
Well, I think you're quite right in describing what the current state of astronomical opinion is on that problem, and I think there are approaches to address that problem from not only with the Hubble Space Telescope, but with other astronomical telescopes. I think that what you have to think about with Space Telescope is not any particular problem. I think if you think about the suite of problems that we have addressed today, none of them were the central problems that we designed Space Telescope to deal with, but all of them are fantastic advances. And I think you have to think of Space Telescope as an observatory, a multi-purpose observatory, which can solve different problems, whatever are the most exciting problems accessible to that instrumentation at the time. And it may not be that the Hubble constant is the most exciting or the most accessible problem for Space Telescope at any given time, but there are a fantastic suite of problems that we want to answer with Space Telescope, and astronomers just stand in line to get their chance to take a crack at the most vulnerable of those problems at a current time.
Okay, next.
For Dr. Moran or anyone, could you tell us what chief things, if any, that you had hoped or expected to accomplish in the first 2 years with this telescope have you not been able to do?
Well, I think if you go way back, Sally and I have a close colleague, John Brandt, who's been instrumental in helping develop the payload of Hubble, who's spent his whole life studying comets, and he got into Hubble in hopes that we might launch in time to see Halley's Comet. And of course, that's one we missed for a variety of reasons.
He'll get it next time.
He'll get it next time, as Halley says. He did get Comet Levy. He and other astronomers saw Comet Levy very early on in our mission. And
Steve, I would have guessed that the one that astronomers were most disappointed was the inability to photograph the fuzz around quasars, because if the mirror for Space Telescope had worked as we had hoped, we would have been able to tell whether quasars, which are the brightest objects in the universe, reside in young galaxies or in old galaxies, and we would have had a hint as to the process by which this most energetic phenomenon occurs. And it's for that reason that it's for that particular observation that I'm most intensely looking forward to the repair mission in 1994. I personally, at least.
or late 93.
Late 93.
John.
John Holloman from CNN. It's a similar question to Dale's question here, and it's Dr. Bacall, you talk about the great presents that all you kids at the birthday party are getting already.
Please don't tell my mother about it.
what kind of presence are you going to be able to get that you're not able to get today when this thing is fixed?
Well, just that. That's precisely it. When the telescope is fixed, we will be able to take pictures with much greater acuity, with much greater resolution than we currently have. And we will address questions like how do the brightest objects in the universe shine, because we will see the stuff around the quasars.
We will be able to see things that are much, much fainter than we can see now. The essence of the issue, what we've lost, is the ability to see the faintest things in the universe, because the slight smearing of the light just makes it more difficult to pick out the very faintest things. And we thought we were going to find the most distant quasars in the universe, where we still are, but we haven't done it yet. In fact, that was the project I was supposed to set out to do, and I was just devastated by the realization that we wouldn't be able to do it. And yet, I've seen now this incredible determination and energy that the thing is going to be not only fixed, but it's going to be improved. And in fact, after the servicing missions, the imaging capabilities of Hubble Space Telescope will be better than they would have been initially because of improvements in the instrument that will go up.
And there's another aspect of that. All of us doing this great science now have to work with about 25% efficiency because the light is spread out over a larger region. So even when we study things spectroscopically, not just taking pictures, we'll be able to do that with much greater efficiency. So we should we should be able to get 4 times as many presents per birthday party as we are now when it's fixed.
And one follow-up, when is it going to be fixed to your satisfaction, based on what you know about repair missions and all of that?
Well, the schedule right now is November '93. And the effort that people are putting in to maintain that schedule is truly awesome to me. I as an astronomer, I really do appreciate the hard work that folks are going to try to get this job done, because everybody wants it desperately. And it's not only the enthusiasm of looking forward to getting it done, but it's the accomplishments that we've seen the last 2 years has so much whetted our appetite for even what more there can yet to come, that we're looking forward to the greatest birthday party that we could conceive of, because now we have a taste of what that cake's going to be like.
Paul?
Paul Hoverston, USA Today. Dr. Heap, a couple questions about this hot star. How hot is it let's say, in comparison to the sun? And second of all, what do you know now, having found this? I mean, what does this tell you more about galaxy formation, or that you didn't know before? In fact, what's the significance having found this?
Well, the sun is about 6,000 degrees, so this at 200,000 degrees Celsius makes it more than 60. I can't do the exact math in my head.
33. I was
33.
Something like 30.
Okay. Times hotter than the sun. And I would say that its basic importance is that it has helped to confirm the theories of stellar evolution. There's been a long-standing theory by Bepaczynski at Princeton about the evolution of stars like the sun, what they would be like, and there has been this prediction that some of them will become extremely hot. And unfortunately, those stars that become extremely hot, they only do so for a very short time, so it's pretty hard to pick them out. And then what's even harder is then that they're hard to see. And so this is one case now where we can say, yeah, this is just what the theory predicted.
Okay.
Okay. Tom Siegfried, Dallas Morning News. For Dr. Bacall, I didn't catch if you gave it the designation of the galaxy with the 10 billion solar masses. And my question about it is, what does your mass measurement tell you about the mass-light ratio and implications for amount of dark matter in omega?
Okay. The reason why you didn't catch the designation of the galaxy is that I don't remember phone numbers or galaxy designations very well. But if you come up afterwards, I'll give you the right phone number. It tells you that the mass-to-light ratio for this galaxy is about 12 in the B band, technical B band, which means
Blue
that
light.
blue light, which means that it's about like the mass to light ratio as you find for ordinary globular clusters in our own galaxy, and therefore there isn't any dark matter in the center of this galaxy to very high precision.
Okay, next, please.
Jim Slade, ABC. Dr. Heap, to flog this horse just a little bit more, it was an interesting comparison to the sun, but what is the comparison in terms, what makes this gee whiz and compared to the star average heat?
Star average heat. I didn't quite hear that.
Jim, could you repeat that?
You know, you gave us a number there, why this was so interesting. Tell us what the average temperature you're talking about in comparative terms. We know the sun is sort of a minor star compared to what you guys are looking at every day.
Well, the typical star, your garden variety star, is the sun, 6,000 degrees. The stars in R136A, these very hot, massive stars, they're 50,000 degrees. Normally, we think that's the range from maybe 1,000 up to 50,000 degrees. But there is a certain class of objects called central stars or planetaries where they can have the full range from 1,000 then all the way up to perhaps 1 million, only they wouldn't be that way for more than 5 weeks.
We'll take 2 more questions here before going to the Institute for Space and Terrestrial Science in Toronto, Ontario. 2 more.
Jan Rohn, Schweizer Handelszeitung, for John Bacall. John, if you are putting all those findings together in one basket, could you please try to outline the cosmological model those findings are best in tune with?
Okay, I think there's one simple result which is easy to overlook, but to me is absolutely awesome and is almost presumptuous, that comes from these results. And that is, back to the very edges of the universe, the laws of physics, which were formulated in the 1930s by Einstein largely, seem to apply. And there's not a great deal out there that we didn't already know about, at least in a condensed form, which, such as in galaxies or other things where a lot of matter is there. So for me, it's humbling and awesome, and you know, it makes you feel very modest that it's possible to have, in 1930, anticipated the way things would behave based on pure reasoning here on a absolutely negligible part of the universe about what huge things how they would behave at the very earliest times that we know about in the universe. So I would say that everything that we know about is consistent with the cosmology that was developed by Einstein and Friedman back in the 1930s, and fits very well. And you may find that not surprising, but I think we had no right to presume that, and it's awesome to me that the human mind has achieved that kind of synthesis.
I have a little follow-up. Tell me, if you would have to put your finger on the open or the closed model, which way would you go?
Gosh, are you talking about Monday, Wednesday, and Friday, or Tuesday, Thursday, and Saturday? I have no opinion.
Okay, Earl, and then we'll go to Toronto.
Earl Lane with Newsday. I was wondering if Dr. Heap might be able to expand a little bit on why in this R136A you found so many heavyweights as opposed to lightweights. I mean, is that still fit in within the cosmology that Dr. Bacall was just talking about?
No, it doesn't have to do with cosmology, but it has to do with star formation. It's an interesting question to me why this happens. The easy way is to say it's either heredity or environment.
Are you absolutely sure that if there were things which were not very bright and very massive there, that you wouldn't have missed them?
Yes, that's a possibility. And so we did tests. We said, okay, let's take the picture, and now let's add some fake stars on that would be like the less massive stars. Could we detect them? And we found out that no, we couldn't detect the very lowest mass stars, but we could detect ones of intermediate mass, and we don't even see those. So we're pretty sure of our findings. But to get back to your question, I think what's important is that we find out how stars form and why they form the way that they do. What we're seeing now is that stars in another galaxy are forming in a different way than they are in our galaxy. Well, the Large Magellanic Cloud, the galaxy that R136a is in, is different from our galaxy. First of all, it's a more primitive galaxy. It hasn't had as many generations of stars to build up the heavier elements. That's going to affect the way stars form.
I think Sally may be being too modest, though, about the significance of this kind of discovery. You heard John Bacall talk about dark matter. We don't know what it is. Sally's found a place where preferentially very massive stars form. Those stars are not going to live very long, and when they're dead, they're going to be dead, very massive, dark stars. They're going to be large, massive accumulations of dark matter. If that happened enough times in the universe, it could go a long way toward explaining the mysterious dark matter that John was talking about. We need to explain some cosmological issues.
Are you suggesting R136a is going to become one big black hole?
No, nope. Lots of little dead, massive stars, probably collections of neutron stars or denser things than that.
I don't think that there's enough of the visible stars around to make a significant dent in the dark matter.
But that's why the point is, if they preferentially formed in a more massive configurations, it's an example of what she was showing us, and that had happened in a large measure early on in the universe, there would have to be a great deal of their corpses around. So that was the issue in which I was trying to draw the connections.
It's pretty far off quantitatively, I think.
Yeah. But because it occurs in a galaxy that is more primitive, maybe that's the way star clusters formed here in our galaxy. And maybe, as you say, these stars popped off. Maybe we are here in the Milky Way long after the party was over.
The real answer to this gentleman's question, let's be fair, as to why are more massive stars forming here than in our own galaxy is very simple, and it's nobody knows. Right? That's really the point. We don't understand how clouds fragment down into individual stars.
We almost talked around that.
We thought we had it figured out in the Milky Way. We thought that mostly you form small mass stars, because that's what we see in the Milky Way. Maybe we couldn't write it all down, but we thought the problem was settled, and now she has the bad taste to come along with a cluster that does exactly the opposite, and that's why it's interesting.
But it shows that this is an area where observation leads the way. You can't make assumptions anymore that the star clusters elsewhere are just like the ones here in our own galaxy.
That's quite right.
We weren't present at the creation, and we're going to have to play catch-up.
And with that, one more question before we go to Toronto.
I'm Mary Miller from CONUS. At the risk of bringing this to such an elementary level, and I apologize for those of us who are reporting to the average layman out there, I'm wondering maybe, Dr. Moran, if you could sort of sum up two things in the realm of all of your discoveries, if you put some perspective on these two new ones today, whether these are considered revolutionary or what. And secondly, to the average person out there who says, what is all this worth? You know, my taxpayer dollars going for this. What does it mean to the layman out there that you have made these discoveries?
Okay, let me
A, a perspective, B, a meaning and a justification.
Let me take the second question first. I think, first of all, the layman and especially the taxpayer should know that, as you've seen today, the astronomers are very excited about all of the exciting things they're learning from Hubble. We want to fix it and make it do the total job it was designed for, but there isn't time or money that's going to waste. I think at a deeper level, the reason that our nation does things like this, and I should add, the European Space Agency also contributed mightily to the development of the Hubble telescope, goes back to why we do basic research in the first place. It's not the applied research that you expect to go directly to your corporate bottom line or your gross national product, but it is the kind of endeavor that opens people's minds, both the grown-ups we have on the panels and in the universities around the country, and the kids in in school and the kids that should be in school. And what we find as we look around the world, I think at the present day and as we look back over history, that the societies that move forward and go ahead are the ones where they have good education, where learning is valued, and where when you have obtained your education, you can put it to use in research and exploring the unknown. Then getting back to the new findings that were announced today, I must say that there's probably a few reporters out there. I think John Wilford's listening on an audio link in New York who had been led to believe, because that's what I thought, that we were going to concentrate on all the good stuff we've learned over the last 2 years, and that the new things we'd be announcing would be examples of what we're finding every day, and not necessarily some of Hubble's greatest hits. But as it's come out, and as I've heard the comments of experts who did the work and experts who didn't do the work and are just been learning about it, in some cases since yesterday, I think that two things we've heard about today have potential to wind up eventually in the textbooks as very major findings. And one of them is this star cluster that really confirms what we've been thinking for a year or two since we first started looking with Hubble, that stars, and maybe before there was some suspicion, some stars can form in ways or in groups very much unlike what many of us might have expected. I think for every finding that you get, there will be a theorist out there who may have approximately predicted it, but once again, there's a difference between having a lot of theories and having an observation that helps us narrow down the knowledge of what is going on. And the other one is something that John Bacall told us that had two parts that we didn't know till today, or maybe in my case last night, and that is that he's been able to measure the very dense central core of a galaxy to actually determine its mass with a precision of 2%. I'm not sure that I can measure my mass on the scale at home with that precision. I'm not sure I want to. And the other thing is the corollary of that finding that came out in the question period, and that is that he believes that you have enough light so that there are enough stars in the center of that galaxy to account for all that mass that's bending the light of the distant quasar and making this four-sided, four-point image of the gravitational lens image of the distant quasar, that wherever he really looks hard for dark matter, he's not finding much. And yet there are lots of cosmological theories out there that differ only, and they can't agree on what kind of dark matter makes up 90% of the universe. Well, the harder we look, the harder it is to find. And I think that is a really significant result, even if it ends with a question.
Okay, do we have any questions from Toronto? This is where the Home Institution from Dr. John Caldwell. You saw the videotape earlier.
Michael Smith, the Toronto Star. When the repair mission flies late in 1993, will there be any aspects of the repairs that will not be able to be done?
Do you want to tell us who should answer that?
Let's see.
I missed the question.
Can we repeat that, please?
What will the repair mission
Sure.
not be able to do in
When the mission flies in 93, will there be any aspects of the repairs that will not be able to be done?
John, you indicated that.
I think that the mission, if successful, will accomplish all of the highest priorities goals that we as astronomers want to see accomplished. The things that are most important to fix on HST will be fixed. The things that will keep us going with frontier discoveries over the next decade could be repaired at the end of 93 or the beginning of 94. But I'd like to come back, can I, just for a second, to this question of what the reporter who wanted to address the question of what to tell her readers was really the reason.
TV viewers.
TV viewers what it was that Space Telescope was doing that was of importance to them and why they should be interested. And I think that's a very easy question to answer, because everybody that I encounter, from the person that's the checkout counter at the supermarket to the person that puts gas actually in our car in Princeton, are interested in, and when they hear I'm associated with Space Telescope, ask me, have we found any other people out there? They ask me how long we're going to be around, what's about this strange galaxy, what there is at the end of the universe, what there was at the beginning. They are all asking questions about what there is out there. And it turns on the youngest people and the most curious of all ages. And it's that kind of curiosity which keeps people in science and mathematics and technology in general. And it's a source of pride for our country. It's also something which makes our country stronger, because we are able to compete in the technical areas. So I think if you just tell them about the wonderful things that we're finding, you'll find an enormous interest in the person that puts gas in your car or the person that's checking you out at the supermarket.
Okay, so good. Any more from Toronto?
That was very interesting. It's Mike Smith from the Toronto Star again. But I wonder if someone there could just sort of list what won't be done, rather than say the high priorities will be done.
Well, in fact, the virtually all things will be done. There is a complete replacement camera to take even better images than the ones you've been seeing today. There is another instrument which is going up that will simultaneously correct the other camera and the other two spectrographs. So all the capabilities will be fixed.
We would like to have new instruments on the telescope in the same way that you would not like to have to use the television set that you had bought 10 years ago. We don't want to have to use the instruments that were designed and built and launched on the Space Telescope the first time. But those instruments are not built yet, the new generation, and that will be for the next service mission, when we'll have the best instruments that we can build now. But I think Dan is absolutely right. Everything that we can imagine that we know how to fix now will be fixed on this mission.
Everything that we need to fix.
Yeah.
Okay, any others in Toronto?
Yes, we have one for the question.
Go ahead, please.
Yes, hello, Peter White from SIDS Canada News. I'd like to find out the significance of the aurora observations that have been taken with the Hubble, and significance of other planetary images that have been done.
Well, there are two different categories. The significance of those auroral observations are primarily going to be in terms of helping to understand the magnetosphere of Jupiter. Jupiter has an extremely intense magnetic field, very, very extraordinary radiation belts surrounding it. And trying to understand the mechanisms whereby that magnetic field is guided and generated is the fundamental underlying objective of trying to understand the interaction between Io and Jupiter. In terms of the other imaging observations,
and thereby to shed light on our own
on our own magnetic field of the Earth, which we don't. That's exactly right, which you don't understand either. Other imaging observations of other planets, Saturn, Mars, and Jupiter, are being undertaken as kind of a weather forecasting mechanism. It's the Hubble Space Telescope is the only thing we have now that can take good quality imagery of the distant planets, because these Voyager flybys and so on that produced images in the past are long gone. So if we want to monitor the changes, how do the cloud flows on Jupiter change? How do these incredible storms get generated in the atmosphere of Saturn? What's the ozone layer on Mars like? The only way we can learn these things is by repeated imagery with Hubble Space Telescope, and those are the kinds of observations that are now being made in terms of these planetary survey observations.
And then looking to the future a little, with Hubble in its present condition, we have gotten the best pictures of Pluto and its moon, Charon, that have ever been taken, but they're not quite what we'd really like to understand this most distant and possibly unusual planet. Some people call it a double planet. And with the improved viewing we get from the repair mission with the replacement wide field planetary camera and the CoStar device that will improve the viewing, the other onboard camera, the faint object camera, then we can begin to study the markings on Jupiter, which are theorized to be areas where you do or do not have frozen methane gas that should gradually move around the planet as the distance from the sun increases. Pluto's going away from the sun now, and more methane freezes out. So there's a lot to be done in the solar system, and our Dr. John Brand is waiting for that bright comet to come by that he can search for spectroscopically. He hopes to detect deuterium, the heavy hydrogen from the Big Bang in it, and tell us something about the origin of comets. So I think as to the significance of the auroral observations on Jupiter, you have there in Toronto one of the world's probably 3 or 4 great experts, and he may be too modest to talk about it today except on tape, but I would say that John Caldwell is not the only person who's attempted to photograph the auroral oval on Jupiter, the ultraviolet light. He's done it very successfully, and we're looking forward to him analyzing those images and telling us whether he can validate the theory that the aurora on Jupiter is controlled by particles from the volcanoes on its moon Io.
What I'd like to do now is close for the day, and we'll run the 2-minute video highlighting images Hubble has taken over the past 2 years. Thank you very much for coming. I especially want to thank our panelists, some who carved time off from their holiday weekend to be here with us. Thank you very much.